So what we're going to look at today inside of this video are polar coordinates, and we're going to dive a little bit deeper into polar coordinates than you probably might have done inside of your pre-calculus class, because polar is going to end up becoming kind of important for, or very important for working inside of physics and for working inside of anything where what we have is we have non-straight line paths. So like that especially shows up in physics, right? When we're looking at ellipses or orbits, or we're looking at non-Euclidean geometry. Things like that where it's like, okay, not everything moves on a very flat surface. Sometimes we move in curves, right? Okay. Or maybe we have a path that actually it makes a lot more sense for us to talk about it moving circularly, or we have a special shape that maybe is a little bit better to be described circularly rather than being described in terms of just straight lines. And so that's why we're going to be utilizing polar coordinates. All right. So we're going to go over the basics of polar coordinates. And then we're going to talk about a little bit more in depth about like some of the shapes that we get with polar and also how we go about graphing polar coordinates. So let's look at the base case. So let's first ask, what is a polar coordinate, or what are polar coordinates? So the polar coordinates are where we describe locations in 2 dimensions using the distance that the point is away from the origin as one coordinate, which we'll call r, and the number of degrees, generally in radians, of the terminal angle from the positive axis. And so I'm going to go in here, I'm going to actually get out my graph paper. Okay, maybe a little bit narrower. And so let's actually take a look at what this looks like. So what we're going to imagine is we've got the Cartesian plane, okay, but it's not really actually the Cartesian plane. What it is I've got a set of axes, okay, and I'm going to imagine that these are just generally, they're my x and my y axis, okay, but nothing else is in terms of x and y. So even these grid lines are a little deceptive because we generally think about each box representing a value of 1 in either going in the x direction or going in the y direction. In polar, that's not what's happening. Okay, so let's imagine that I've got this line right here. Okay, I've got this line right here. All right, and so what I want to do is I want to imagine that I first have what is this distance away from the origin, and that distance right there is r. Okay, that's the distance r. And then this angle right there, that is theta. And so how I describe this point is I describe this point as r theta. And there we go. Now, let's imagine, and maybe we'll call this theta 1, because we're going to have another theta. I'm going to show you, and it's going to be kind of similar in many aspects. So now let's take a look at another one. So let's look at this particular line right here, or that particular ray. Okay, and we want to know what this point is right there. And this distance, okay, it is also r. Okay, it's also r, but this angle now is, we'll call that theta 2. So that angle right there from the positive axis is theta 2. Okay, so now what we have is we have r theta 2. And that's a different point. It's a different point in space. Okay, it's basically, we've got the same distance, all right, away from the origin, which is our r, but we have 2 different angles, okay? Now, conversely, we might actually also be able to look at another set of lines, okay? And let's say, for example, I have this line right here, okay, or this point, and it is r distance away from the origin, and it is, we'll call it theta, is the angle that we are away from that positive axis. So this we'll call r theta. And what I'm going to do is I'm going to call this now r1. So r1 is that particular distance. Now what I want to imagine is, let's say, for example, I have another point. And let's say that this other point is out here. Now if I look, what I'm going to notice is this other point right out here, assuming that it's all perfect, okay, it's no longer r1 away from the origin. It's actually, we'll call it r2 away from the origin. It's quite a lot farther away. Okay, so we're going to get, this is r2, but it's still going to be theta, is that angle of elevation from the positive axis. So there's theta. Okay, and so that's kind of like the idea. Now instead of, points on the x and y axis where I go over x and go up y, okay, or over x down y, whatever, whether or not we have positive y or negative y, what I'm going to do now is I'm basically going to imagine that I'm going to go out r. I'm going to be r distance away from the origin, okay? And then theta is going to be my angle of elevation, the angle, my terminal angle, okay, from that positive x-axis. Now, we need to define one other thing, and that is that if we actually have this idea of a negative r, okay? Now, it's a little strange because remember r is the distance away the point is away from the origin. Now, negative r, well, it's still r away from the origin. What we're going to say is that what negative r is, or let's say call this negative r1, negative r1 is actually the distance r with that theta, but what we're going to do is we're going to then flip it over the x-axis, okay? So like, for example, let me show you an example. We can kind of look at this. Let's say, for example, that I have the point, let's call this 4 pi over 2, okay? Now, negative 4 pi over 2 is going to be, or actually that's 5 pi over 2. Let's call that 5 pi over 2. Negative 5 pi over 2 is going to be down here. What I'm doing here with negative r is, or if r is negative, we should say. Not negative r, but like if r is negative, we will flip the point over y equals x. So basically, we're going to flip it over the origin. All right, we're going to essentially, yeah, that's exactly it. We're going to flip it over the origin. So for example, let's say I have this, and we're going to have this be 3 comma pi over 4. So there's 3 comma pi over 4. And so negative 3 pi over 4 is going to be down here. So this is going to be negative 3 pi over 4. And so it gets flipped over that origin. Okay? So there's negative 3 pi over 4. And how I imagine that happening is I've got an angle, call it a vector, all right? And there's that angle. And what I'm going to do is I'm just going to revolve it. I'm going to revolve it 180 degrees. Okay? So basically it becomes a reflection. Or you can even think about it, like I said, as a revolution 180 degrees. You see that with 5 pi over 2 or negative 5 pi over 2. Okay? We can also think of that as a revolution of 180 degrees. All right? So there is actually such a thing as a negative r. Even though we've kind of defined r as being the distance that the point is away from the origin, when we have it being negative, we're going to find the positive one and then flip it. Right? We're going to do that rotation, that 180 degree rotation. And that's going to come out, what that ends up becoming really important for is things like complex numbers, where we start thinking about multiplication in terms of rotation, okay? And even some work inside of polar where we're going to start thinking about rotation as in terms of multiplication. So let's look at some examples. So let's start out with one, maybe like a unit one. We're going to get 1, and we'll do 1 pi over 2. So 1 pi over 2, we're going to imagine we've got pi over 2. Okay, there's that angle. And we're going to go up 1. Okay, and so that's the distance from the origin. So here's 1 pi over 2. Then we can imagine, let's say, for example, we do negative 3 pi over 2. And so for negative 3 pi over 2, what I'm going to do is I'm going to go up 1, 2, 3. Okay, there's 3 pi over 2. And then I'm going to revolve around, or I'm going to flip it over that x-axis. I'm going to reflect it. Okay, so this is now negative 3 pi over 2. How about 3 pi over 4? So if I take 3 pi over 4, let me erase some of these lines. What I'm going to do is I'm going to say, okay, well, let's take 3 pi over 4, and I generally like to do my angles first. Okay, so 3 pi over 4 is going to be, it's here. Okay, there's that 3 pi over 4. Okay, and then we want to go 6 out, and so like I imagine, okay, there's about 6. Is it exact? No, it's not exact, but it's pretty close. And so there's 6 comma 3 pi over 4. What about, now we can imagine going from 0 to 2 pi, what if we go more than 2 pi? Okay, so like, let's say for example, I want to go 3 pi. Okay, so let's say I go 5 comma 3 pi. Well, all I'm going to do is I'm going to rotate multiple times around the unit circle. Okay, so we're going to go, there's 1, there's 2 pi, and then here's 3 pi. So 3 pi ends up back at 1 pi. So there's 3 pi, and then I'm going to go over 5. So there's 5 comma 3 pi, because we're going to rotate around those 3 times. What about, say for example, -4, and we'll do, it's 10 pi over 6. So we got 10 pi over 6, or what is that, 5 pi over 3? So -4 comma 5 pi over 3. So I'm going to go 5 pi over 3, and so that is just a little bit more. It's right about here. That's 5 pi over 3, right? Okay, there's that angle for 5 pi over 3. And then I'm going to go down 4. So let's say, for example, there's 4 5 pi over 3. But wait a second, this is -4, so I've got to go the opposite direction. So I'm basically going to be somewhere around here. Maybe even a little closer. And so there's 4 comma 5 pi over 3, because I've got to now reflect. I've got to do that reflection or that rotation of 180 degrees. And so that's how we actually go out and we graph our polar coordinates. All right? My general way to go about doing this is I like to think in terms of the angle first, figuring out what my angle is, and then calculating the distance that the point is away from the origin. And then if I have to reflect, then I reflect as the third piece. Right? So generally, as a rule of thumb, if I'm graphing, I'm going to find the terminal angle. Second, calculate the distance, the positive distance from the origin, and then I will rotate or reflect as necessary. And that's just how I go about doing it. Can you do it other ways? Absolutely. Whatever way makes you feel comfortable, okay? But that's just systematically, that's how I kind of work. Now that we have a way of representing polar coordinates and talking about polar coordinates and kind of an understanding of what they are, now we want to kind of dive a little bit deeper into what they mean, and also to compare them to our normal way of expressing coordinates using the Cartesian coordinate system, which is also called the rectangular system. So we're going to look at the polar versus rectangular. So coordinate systems are just different ways of communicating locations in space. They're like naming conventions that allow us to demonstrate where something is graphed or where something is located in 2 dimensions. On the one hand, we have over x up y, okay? On the other hand, what we have is go this many degrees away from that positive x-axis, and then go this far distance away from the origin, okay? And so what we want to do now is we want to look at what is their relationship, because they're obviously related, and we also want to be able to kind of like translate rectangular into polar and polar into rectangular. So let's take a look at that. So what we're going to do is I'm going to imagine, okay, I've got this point right here, okay? I've got this point, and this point in rectangular space is 1, 2, 3, 4, 5. It's 5, comma, and it's 5, comma 5. Okay, 5, comma 5. And so that's my rectangular space. Now what I'm going to do with this is I'm going to generate a triangle. All right, I'm going to generate a right triangle. And there that is. And so what I'm going to do now is I'm going to kind of zoom out that triangle to kind of talk about what r is going to be and what theta is going to be. Most likely you've seen this before, but let's at least get it really very clear, very concrete. So this is 5, and this is 5. Okay? Now, this distance right here, that's this distance on our Cartesian coordinate plane, and if we recognize that that's r, that's how I generated and I showed r. So what is r going to be? Well, in our case, r is going to equal the square root of 5 squared plus 5 squared by the Pythagorean theorem. By either the distance formula or the Pythagorean theorem, right? The two of them, by the way, are the same thing. So basically what we've done is we're going to take the square root of our x-coordinate squared plus the square root of our y-coordinate squared. All right? And so if we generalized it, that's exactly what we're going to do. We're going to generalize it. R is then going to equal the square root of x squared plus y squared. And that's what r is. Now, what theta is going to be, notice this here is theta. What we're going to do is we're going to use a little trig here. Notice that we've got the opposite and we've got the adjacent. So theta is going to, or excuse me, the tangent of theta is, in our case, going to be 5 over 5. Okay, now the opposite, by the way, is y, okay, over x. The adjacent being x. So y over x. There we are. So what we're going to do is we're going to say, well, then theta is going to be equal to tan inverse of 5 over 5, which equals tan inverse of y over x. Okay, so what that means is that theta is going to be tan inverse of 1, which equals pi over 4. It also equals, pi over 4 plus 2 pi plus pi k for k belonging to the integers. And there's a couple things that we have to get here about these coordinates. All right. One, I've got r is going to be x squared plus y squared. That's pretty straightforward. And so when you're in rectangular, you're generally going to be like expressing that one. We're generally going to be expressing that one as positive, right? Okay. If we get a negative r, like we're given a negative r, then we know how to reflect it, that sort of thing. But given this particular formula, you're always going to end up with the r being positive. Now, there's an issue here, though. And the issue here is, notice that this is plus pi k, okay? Because tangent has a period of pi, right? So if you kind of think about it, not only does tan inverse of tan inverse of 1 equal pi over 4, it's also going to be the same value if it was down here, okay? And so what that is that's 5 pi over 4, or 5 pi over 4. Right? Which is actually plus the pi k. So how do you know which one it is? Okay? Well, you've got to take a look at your x and y's. Yes? You've got to look at your x and y's because this is going to be depending on the quadrant in which the coordinate lies. So if what we're looking at is we're looking at -5, -5, right, which is this thing down here, then we're going to use 5 pi over 4. On the other hand, if we're looking up here, like 5, 5, we're going to use pi over 4. So you're actually going to have to be pretty careful about which one you're looking at, okay, or which one you want. Because again, the same thing. R, since we're squaring x and y, you're not going to actually be able to tell, right? It's just going to be the square root of 25 plus 25, square root of 50, right, which is 5 root 2, okay, which by the way is our r. That's equal to 5 root 2. So consequently, you've got to be careful about which quadrant your rectangular point lies in when we're converting from polar into rectangular, okay? So just as a way to kind of like review that, what we'll do is we'll say, okay, well, r is going to equal the square root of x squared plus y squared. Nothing needs to be done there, okay? Just basically using that distance formula. If we imagine we've got a triangle, a right triangle, I'm going to use one that's actually in the first quadrant. Here's there's y, and here's x, and here's r, and here's theta. Then theta is then going to equal the tan inverse of y over x. Okay? Depending on the quadrant. So it'll still be the same theta. You might have to change what that theta is. You might have to add a pi to it. If, say, for example, we've got 2 negatives instead of 2 positives, or for x and y, or for example, if we're in quadrant 4 versus quadrant 2. Okay? So kind of let me give you an example. Let's say, for example, we look again. We'll draw a picture of this. Okay? And let's say I am down here at 2, 4. All right, so we're down at 2, we're at 4, -2. All right. Now r is going to equal the square root of 4 squared plus -2 squared. Okay, and so that's the square root of 20, which equals 4 root 5. But now I need to figure out, if I imagine I've got my here, this is now theta. There's theta. Okay, But when I take tan inverse of, in this case, negative 2 over 4, okay, which is tan inverse of negative 1/2. Now when I plug it into my calculator, what I end up getting is I end up getting negative 0.463647, somewhere thereabouts, which actually is this because my calculator, right, calculates tangent from negative pi over 2 to pi over 2. Okay, right, basically gives me just that one rotation. Now, what I'm going to need is if it was over here, say for example, instead, what I had was I had negative 4, positive 2, okay, negative 4, positive 2, then I would have had to gone in and added pi. So this one here, okay, for negative 4, positive 2, is going to be in polar. It's going to end up being 4 root 5. It's got the same distance, okay, but its angle now is going to actually be negative 0.463647 plus pi, because I've got to calculate the additional pi. All right, and that's because inside of my calculator, when I use tan inverse, it calculates from negative pi over 2 to pi over 2. Okay, for this one, we can actually just go directly from my calculator. So my polar here is going to end up being 4 root 5, comma, negative 0.463647. Okay, and that's actually how we go about finding the values for r and theta when we're given rectangular coordinates. For us to transform polar into rectangular form, what we're going to do is we're going to have to play on this idea that what we're looking at is we're looking at a circle. Okay, and that's the polar coordinate system is basically looking at a set of circles. And what you want to imagine is you basically got the unit circle. All right, but you've got the unit circle with multiple, they look like these rings. All right, you'll see them, they look like these rings, like, so that's one that has a radius of 2, here's one a radius of 1, here's another one with a radius of 3. Probably not the greatest picture in the entire world, but you kind of imagine that we've got these concentric circles, and if you put this point right here, it's got an r of 3, and say it's got a degree measure of, I don't know, 65 degrees, right? Whatever that would be inside of radians. And so there it is. Now what you want to notice is that everything that's on this circle, okay, has that radius. Okay, it has that radius, and in fact, we can imagine that we have a triangle. Okay, we have a triangle, and these triangles, they're all similar triangles. Okay, so every single one of the triangles is a similar triangle. So basically what we can do is we could say, okay, well, I want to imagine if I had, if we said, okay, so on the unit circle, right, we have a radius r equals 1. Okay, so on the unit circle, we're going to end up having a radius equal to 1, and x is just going to equal cosine theta. Okay, so what we can do is we can say, well, x over r is going to equal, right, cosine theta over 1. And there we are, right? Because that's just a ratio for similar triangles. And conversely, if we look on the unit circle, that y equals, we say, is going to end up being sine theta. Okay, so y over r, y over the radius is going to equal sine theta, right, over 1. And this is, y only equals sine theta on the unit circle. Okay? So what we want to do is we kind of imagine what these triangles look like. All right? Let's say here's a triangle that has a radius equal to r. Okay? And this is, say, for example, there is its y, and there is its x. Okay? Conversely, if we had the exact same triangle, but now we're on the unit circle, okay, here's the 1, there's its radius, okay, this is going to end up being sine theta, right, that's my y, and cosine theta is going to end up being my x, okay, so all we've got to do is we basically got to just set up a ratio for similar triangles, and that will end up actually giving me the values for x and y in terms of polar. All it takes now is just a little bit of algebra. So x, right, over r is going to equal cosine theta over 1, which means that when I multiply both sides by r, x is going to equal r cosine theta. Conversely, if I have y over r equals sine theta over 1, then y is going to equal r sine theta. Right? And that's just a continuation for trig. You may actually remember that from trig, that if you change the radius of the circle, in order to find your x and y coordinates, all you've got to do is just multiply the cosine theta or the sine theta by the radius of the circle. Right? And that's because we have these similar triangles. Okay? And so those are the ways that we actually can transform polar coordinates into rectangular coordinates. So looking at an example, let's say, for example, I have the polar coordinate 3, 4 pi over 3. So x is going to equal 3 times cosine 4 pi over 3. And y is going to equal 3 times sine of 4 pi over 3. So we think through, what is 4 pi over 3? So this is going to end up being 3 times, and then this will be 3 times 1/2, so that equals 3 halves. And this one is going to be 3 times the square root of 3 over 2. And so that equals 3 root 3 over 2. So the rectangular coordinate is 3 halves, comma, 3 root 3 over 2. But you know what? We do have something here. So the sine pi over 3 is actually negative. So this should be actually negative. So this should be negative 3 root 3 over 2. As should also, this should be negative 3 halves. So it should be negative 3 halves, negative 3 root 3 over 2. And actually, as a check, one of the ways that I actually kind of figured that out was to say, okay, well, where's 4 pi over 3? Here's pi, right? That's 3 pi over 3. 4 pi over 3 then is going to end up being, right, it's kind of somewhere in here, right? So that means that x and y are both negative. Hence, I had to go through and check my trig for a moment. All right, but that's it, right? X equals r cosine theta, y equals r sine theta, and that actually gives us the values of our rectangular coordinates if we already know the polar. Now let's take a look at something that's really interesting, but can be kind of tricky, and that is graphing polar equations. When what we're given the polar equation. Now, sometimes some people like to go out and they like to transform the polar equation into a rectangular equation. And while that makes sense in some cases, in most cases actually it doesn't. Because the reason why we're using polar is because polar is a better representation of these particular graphs. And we're going to look at some of them that are actually going to be, kind of like they're canonical polar graphs that if we tried to represent them in rectangular, they wouldn't make a lot of sense and they would actually be pretty difficult to kind of explain, but they're pretty, what we call, elegant inside of polar, all right? But let's first start out with some simple ones. Let's start out with this one. Let's start out with r equals 3, okay? So r equals 3, and so if you think about what this means, is this is the set of all numbers that are 3 away from the origin. So in this case, theta does not matter. Theta can be anything. It can be anything, okay? It's running free. And so all we need to know is that for any theta, we're going to have an r equal to 3. So if I imagine what that looks like, right, okay, what I'm going to do is I'm going to kind of just plot a couple quick points, and then I'm going to kind of think in my mind, I'm going to imagine what happens if I start to, expand out or kind of like connect the dots. So there is 3. That point right there, that's also 3 away from the origin. 3 away from the origin again, 3 away from the origin again. Okay? I might now think to myself, oh, okay, well, what about over here? Okay, it's somewhere in that area, that thereabouts, right? Because we want to get it about 3 away, about 3 away, about 3 away. Okay, and now it should start to become kind of apparent what this is. If you think about it, the set of all points that are equidistant from a particular point is called a circle. Okay, so r equals 3, in fact, is the polar representation of a circle with radius 3. And that's, in fact, exactly what it is. Okay? So if I write this, say, for example, I write r equals k, is a circle of radius k. And there we go. Okay? All right, let's take a look at another example. Now let's look at theta equals pi over 4. Now in this case, what we've got, right, is we've got everything that has a terminal angle of pi over 4 away from the positive x-axis. So we might actually think about, okay, it's anything that's on this line right here. Now don't forget that we can also have negative r's. And so my negative r's are going to go in the opposite direction, right? So every positive r is going to go in that positive direction, and every negative r is going to go in that negative direction, okay? Right? So like, for example, we might have, here's r equals 3, and then we have r equals 5, and we have r equals 10, right? And then we have r equals negative 10 down here. But in each and every case, theta equals pi over 4. So what this does is this actually defines for us something. Theta equal to sum k is the equation of a line. So theta equals k is going to be the equation of a line, right? Anything that's all on the same angle is going to actually end up being on the same line, right? Whether or not we're going in the positive direction means that r is positive, and if we go in the negative direction, that means r is going to be negative. What about this figure? Now I've got r equals 3 theta. Okay, now we actually have a relationship between theta and r. So here's the idea with this. So when theta is equal to 0, r is going to be equal to 0. Okay, and we can even kind of imagine like a coordinate system. I have r and I have theta. When r is 0, theta is 0. Oh, excuse me, when theta is 0, r is 0. Pardon me. So we'll make theta be our independent variable and r be our dependent variable. Generally, that's how it goes when we work with polar. Now, what about what happens if, say, we go now to pi over 4? Well, now, this is r equals 3 pi over 4. Okay? So once I hit pi over 4, I've actually gone, fairly far away. I mean, like, it's almost a full pi away. So it's almost 3. So it's somewhere around here at pi over 4. Okay? And I can kind of imagine what's happening, right? I'm getting further away. Right? Let's say, for example, I now go to pi over 2, and now I'm at r as 3 pi over 2. Well, that's pretty significant, right? That's about 5. We get further away from the origin, okay, as we circle the circle, right? So as I increase theta, right, as theta goes up, so does r. R increases as well. So we get further away as theta goes up. So what happens is we get something that kind of looks like this. Right? We're spiraling outward away from the origin. Okay? And so that's what a spiral looks like. Right? We're going to connect r and theta in a very linear fashion. As theta goes up linearly, r is going to go up linearly as well. So this function, r equals k theta, is a spiral. Okay? And we kind of see what that relationship is. Kind of a neat relationship. Now, let's look at another example. Let's say, for example, that what I'm looking at is I've got r equals 2 cosine theta. I got r equals 2 cosine theta. Now, I look at this, I now have a trig function, and this trig function, right, it's periodic. So cosine theta is periodic. And so consequently, what's going to happen is that my r is going to like kind of curve back in on itself, right? Every 2 pi, right? It has a period of 2 pi. And so what's going to happen is we're going to have something that looks like a closed circle because every time I go 2 pi, I'm going to actually end up with the same values. Okay, that kind of makes sense. So all I really need to do is I need to just look at like a period of 2 pi in order to like kind of figure out what the entirety of this figure is. Now, in order to kind of understand that a little bit better, what I'm going to do is I'm going to draw a picture here, okay? All right, and I'm going to imagine the cosine theta graph, but I'm actually going to imagine 2 cosine theta. So I'm going to imagine if like what I was looking at here was just like y equals 2 cosine x, right? Okay, so we're going to make this is going to be the theta axis, and this will be the r axis. And I'm actually going to draw a picture of my trig function. So it's going to have, right, let's say here's 1, here's 2, here's -1, and here's -2. And it's cosine theta, so we'll start out, here's pi over 2, here's pi, here's 3 pi over 2, excuse me, there's 3 pi over 2, and here's 2 pi. And so I'm going to move downward, and I'm going to imagine that cosine graph. Okay, so there's my cosine graph, and it does that, right? Okay, and it's just going to cycle back in every 2 pi, so I only really actually need to get a single period. Now what I'm going to do is I'm going to convert that into rectangular, just to help me kind of understand what's going on in, or not into rectangular, but excuse me, onto our polar graph. So this is where we take r and theta, we make it rectangular, and now we're going to turn it into our polar graph. So when theta is 0, here's my r-axis, so when theta is 0, so there's theta is 0, r is 2. So we're at 0, 2, 2, 0, right there, right? Okay, r theta, 2, 0. And then when I go to pi over 4, I could see that my r is 1. So now I kind of imagine, okay, there's pi over 4 and it's 1. When I'm at pi over 2, we're at 0. Okay. When I go down to 3 pi over 4, I'm now at what? Negative 1. Okay, you can see there it's at negative 1 for pi over 4. Okay, so we're kind of moving down this way. Okay. All right. And now when I get down to pi, okay, I'm at pi, I'm actually going to be at, down at the bottom, I'm at negative 2. Excuse me. There it is. I'm at negative 2. Okay, great. And which is kind of interesting because here's pi, right? Here's pi. There's the pi direction, but it's negative 2, so it's actually got to swing backwards. So it's got to go in the backwards direction. So what we're seeing actually, what's happening here is that in this graph, yes, the period for 2 cosine theta is a period of 2 pi, right? Okay, but in order for us to get the entirety of our polar graph, we only had to go around once, okay? Because what's going to happen now is I'm now going to go back, okay? When theta is now what 5 pi over 4. Right, I'm going to end up at negative 1 again, okay? But 5 pi over 4, okay, is over in this direction, and then so when we go negative 1, we've got to flip it back over. We've got to flip it back over y equals x, all right? So what we get here is we get the equation of a circle, but the equation of this circle is actually one that has a different center, all right? It's no longer centered at the origin. Instead, it's centered at, in this case, 1, 0. So what we see is we actually get that r equals a cosine theta is a circle as well, but it's been shifted. And we're going to look at we can actually find the equation for that circle, but it's a circle as well, and it's been shifted. It's been shifted left or right. And although I'm not going to do an example of this on the video, I'm going to have r equals a sine theta, okay, is a circle, but it's shifted up or down. So now let's take a look at this function. Let's look at r equals 1 plus sine theta. And so what I'm going to do the same thing that I did last time. I'm going to create a function. I'm going to have r here, and then I'm going to have theta as being like my x-axis, okay, my independent variable. And it's sine theta, so what I'm going to do is, okay, I'll have my pi over 2, my pi, my 3 pi over 2, my 2 pi, okay? And there's my full period. And what I'm going to do now is, because it's sine, notice this is going to be sine, okay? And it's going to be shifted up 1. So we're going to go 1 to 2. So we're going to shift up 1. And so I'm going to go up, okay, to 0. Oh, excuse me. This is going to go from 0, 1, and then we'll go up to when we're pi over 2, and then back down to pi 1, excuse me, pi 1, and then down to negative 1 comma 3 pi over 2, and then we'll have 2 pi. And notice a couple of things here. Again, same deal, right? Okay, here's now, once we click past pi, okay, right? These are all negative r's. And since they're negative r's, they're actually just going to flip over y equals x. They're going to rotate by 180 degrees. So we're going to actually kind of like rotate back in on ourselves. A lot like what we did last time. Okay? So let's see what exactly happens when we do this. Okay, so we're going to start out 1. There's 1, 0. Okay? And then we're going to go up to pi over 2. And it's going to go, there's 1. Okay? And then I'm going to come back down. Right? Okay? Then I'm going to come back down until I hit the pi value. So it's going to be pi. And it'll be, again, be 1. But wait, these aren't negatives. They're still positives. They're not negatives. They're all positives. They only look like they're negatives. But remember, we shifted everything up 1. Okay? So now I've come back down. I'm now at pi, and I'm at pi 1. Okay? So now I'm at pi 1. I'm right here. Okay? And I'm going to go down, and at 3 pi over 2, I'm going to be at 0. Okay? And then at 2 pi, I'm going to be back at 1. So I have some questions. I'm going to kind of do one of these things right here, okay? And I'm going to move, and what's going to happen is I'm going to get kind of like this heart shape, right? Okay, so as I'm going to be a little bit further away, but I'm going to tuck in, right? I'm going to tuck in a little bit. I'm going to get closer and closer and closer to 1 or to 0 until I finally hit 0, and then I'm going to go farther away from 0 until I get back up to 1, okay? And I'm going to get this thing that looks like a heart. All right, and we actually have a name for it. It's called a cardioid. And a cardioid is represented as r equals a plus sine theta, or r equals a plus cosine theta, depending upon, right, where your heart is. All right, in this case, we have a plus sine theta. It's pointing upwards because that 1 is positive, okay, and it's kind of like an up-down. On the other hand, if we had utilized cosine theta, it would have been turned on its side. Now, what we're going to notice about these, about like things like cardioids and other things, which they have a specific name. They're not just cardioids. This one's called a cardioid, but we have these. They're of a special group. They're a special group called Limpsoms. And I'm probably not stating that correctly or doing that, but I think that's how we pronounce it. Limpsoms, all right? And these are things of the nature of, we write them as r equals a, okay, plus or minus b sine theta, or r equals a plus or minus b cosine theta. And depending upon the relationship between them, between a and b, so depending on this relationship, and also the cosine of the sine, we get slightly different shapes, okay? So like in this case, we get one that looks like a heart, and hence why it's called a cardioid, but we could get other ones that kind of look like, they look like something like this, okay? They don't quite touch 0. We have other ones that kind of like curve in on themselves, right? They have like a little curlicue inside of them, all right? We have other ones that almost look like, they basically look a lot like circles. All right, depending upon that relationship between A and B. And what I'll do is I'll post actually or inside of your book, inside of both your books, you can actually find a listing of those particular relationships, the relationship between A and B, and how it is that we distinguish which kind of limpsom that we're looking at. So now let's take a look at how is it that we're going to now transform polar equations into rectangular ones. And this is basically, it's algebraic for the most part, and it utilizes those definitions that we have. So let's take a look at that one that we had. We had r equals 2, so we had 2 cosine theta. All right, so we had r equals 2 cosine theta, and we already know that that's a circle of radius 1 that, in fact, has its center at 1, 0. We already know that because we actually looked at it earlier. That's what the picture that we got. So we expected that we're going to get something like that. Now remember that r equals the square root of x squared plus y squared. Okay? So r is going to equal the square root of x squared plus y squared. And in fact, we also know that if x equals r cosine theta, then x over r equals cosine theta. So what we're going to do is we're going to utilize those two things in order to actually kind of substitute, and then we're going to do some algebra. So r equals the square root of x squared plus y squared. So we're going to have the square root of x squared plus y squared, okay, is going to equal 2 times x over r. Right? And all we've done is we've just said, okay, well, cosine theta is x over r. Okay? And what that means, though, x over r, well, that's actually going to be, right, x over the square root of x squared plus y squared. And that's going to be cosine theta. So let's change all of that over into polar. So 2 over x squared, the square root of x squared plus y squared. Now what I'm going to do is I'm actually going to go through and I'm going to multiply by the square root of x squared plus y squared. So this is going to be x squared plus y squared equals 2x. So now what I'm going to do with that is I'm going to say, okay, well, that's cool. I can handle that. So I'm going to get x squared minus 2x. I'm going to move all of my x's and y's over to one side, plus y squared is going to equal, and now 0. And now what I'm going to do is I'm going to go in and complete the square. Okay? So 1/2 of 2, right, equals 1, and then we square it, we get 1 squared. So this means that we're going to get x squared minus 2x plus 1 plus y squared equals, and we have to add 1 to the other side too. So now what I get is I get x squared, right? Or excuse me, this piece now, x squared minus 2x plus 1 is, when we complete the square, is going to be x minus 1 squared plus y squared, and that'll equal 1. And there we go. And that is our equation. A circle of radius 1 with, okay, its center at 1, 0. And there we go. After we've done some, conic sections, we know that that's the case. What about, let's do some of the other ones there, okay? So let's go in and let's take a look at another example. Let's look at that other one. Here's our example. We're going to use r equals 1 plus sine theta. Okay? So now we know that r equals the square root of x squared plus y squared. We know that y is equal to r sine theta. So sine theta is going to equal y over r, which equals y over the square root of x squared plus y squared. So now, I plug that back in, I'm going to get the square root of x squared plus y squared equals 1 plus y over the square root of x squared plus y squared. Now this is a heck of a lot harder than the last one, at least algebraically. But first make sure that you're like, okay, I can see the substitution. Not so bad, not so terrible. Okay? What I'm going to do is I am in fact going to get that square root of x squared plus y squared out of the denominator. So I am going to in fact multiply through by the square root of x squared plus y squared. So this is going to give me x squared plus y squared equals the square root of x squared plus y squared plus y. Great. Now what? Well, now what I'm going to do is I'm going to subtract that y over. You've seen these before in algebra. I've got x squared plus y squared minus y is going to equal the square root of x squared plus y squared. And now that I've got this, where I've got my square root all on one side, now I'm going to square both sides. Square with both sides. And this is going to give me x to the 4th plus, and what I'm going to do, I'm going to have to FOIL this whole thing out. Okay, so just for those of you who are like, I hate it when they just shorthand algebra. X squared plus y squared minus y times x squared plus y squared minus y, okay, is going to end up equaling x to the 4th plus x squared y squared minus x squared y plus x squared y squared plus y to the 4th minus y cubed minus x squared y minus y cubed plus y squared. Let's go through it. Just check that. I've got x to the fourth, x squared y squared, minus x squared y, plus x squared y squared, plus y to the fourth, minus y cubed, minus x squared y, minus y cubed, plus y squared. Great. Okay? And that all is going to end up equaling then x squared plus y squared. So now I can, if you notice, I could cancel out my y squareds because you're just going to subtract them. All right. This is going to give me x to the fourth plus y to the fourth minus 2y cubed, okay, plus 2x squared y squared minus 2x squared y, and that all equals x squared. Then what I'm going to do is I'll move that x squared over the other side just to get everything, kind of into the equation form. So I got the x to the fourth. There's x to the fourth. And then here's my x squared, y squared, x squared, y squared. It's the only two. So and then plus y to the fourth. Okay, there's plus my y to the fourth. Just make sure that that's still there. Minus 2y cubed. Okay, there's minus 2y cubed. So just to make sure they're all represented, there's those two. Plus 2x squared, y squared. Minus 2x squared y minus x squared equals 0. Boop. And there's your rectangular equation. It should actually become pretty obvious as to why you'd much rather have that written polar. The polar is so much easier to understand. The polar is so much easier to actually go out and graph. This, I don't know, it's akin to gobbledygook. And getting back to the polar from it would be pretty difficult. So you can kind of see why those polar equations can be very handy, especially for things that are periodic, graphs that are periodic, or that are circular in their nature. Okay, so what we've looked at here is we've kind of gone through the basics of polar equations, how to work with polar equations. What we've done is we've gone through it and we've talked about how it is that we go in first and represent what are the polar coordinates. How do we represent rectangular coordinates as polar? How do we represent polar coordinates as rectangular? Then we started talking about graphing, graphing functions of polar coordinates. And then we talked about how do we transform rectangular functions how do we transform polar functions into rectangular coordinates? Okay, so probably